We're going to start with this problem about rainy day, nice day. It used to be rainy, sunny, but then we started using S for the states. So I don't want to use S. That's why I changed it to rainy, nice. And in this one, the weather depends on the last 2 days. And there's some rules. But the question is it even a Markov chain, right? So we started this class with the snakes and ladders example, which I think is the quintessential Markov chain example. In snakes and ladders, it doesn't matter how you got to a square. Once you're at a square, you know where you're going to go next. And that is like the Markov property, right? That where you go next depends only on where you are, not how you got there. And then we have this like thing with these like complicated rules that look at the last 2 days. And the question is it a Markov chain or not? And let's see what people said. So I think 15 people voted. A couple people walked in a little late. We won't get their vote. We'll see what people said. Okay. So 11 people said yes, it's a Markov chain. 5 people said no, it's not a Markov chain. 1 person said it depends on what the definition of it is. This is like a famous line from like a Bill Clinton scandal, where it's like it depends on what the definition of it is. Okay. Yes, it's a Markov chain, I think is wrong. It's misleading. It's at the very least misleading, and worst case wrong. Because what the weather is on a given day is certainly not a Markov chain. So let me write that down. Let's write that down. Okay, so here is the fact. This is the two-day weather model. Weather model. And here is the fact. If you let, so sometimes we've been using X, sometimes we've been using S. Let's use S. Let's say S sub t, the state at time t, equals either rainy or sunny. Let's say in, that's how we do sets in math. In rainy or nice. This is what we had before when we did the thing we said. On a given day, it's either rainy or nice. We have the sequence of days. This is not a Markov chain. This is not a Markov chain. A Markov chain. Okay, why is it not a Markov chain? And the reason it's going to be is that the next state is going to depend not just on ST, but it's going to depend on a little bit of history of ST. And so very specifically, it does not satisfy the Markov property. It does not satisfy the Markov property. Okay, and in particular, if you look at the probability that ST plus 1, let's say, equals rainy, given ST equals, let's say, rainy. So if you want to calculate what is the probability the next day is rainy, given that today is rainy, this probability is different depending on what happened at time t minus 1. So if today it's rainy and you want to know what's the probability it's raining tomorrow, you don't have a good answer. You need to know 2 things, right? So this is not equal to the probability that ST plus 1 equals rainy given ST equals rainy, ST minus 1 equals rainy, because there's another possibility, right? I'll say it nice. Okay. So if you want to know tomorrow's weather forecast, it's not enough to know today's weather forecast. You need to know the last 2 days. And the Markov property says, in a Markov chain, if you know the state at time t, you can automatically figure out time t plus 1. So in a real Markov chain, if you're given ST, then you can figure out ST plus 1. And this thing that I described with ST equal rainy or nice is not a Markov chain. So if you chose yes, you could be wrong. If you thought that the weather on every day is the Markov chain, that's definitely wrong. The right answer, of course, is it depends on what the definition of it is. Right? So 1 person got it right. So when you say it is a Markov chain, if by it you mean the weather on the day, then you are wrong. So the weather on the day is not a Markov chain. But there is something else. There is a way to rescue the problem, and you can make something that is a Markov chain, And that something will tell you the weather on the day. But literally the weather on the day, ST, either rainy or nice, itself is not a Markov chain. So people who selected no are also wrong. Well, okay. So again, it depends on what you meant by it's. If you, when you selected no, it's not a Markov chain, and you meant this, what I just showed you, then you are correct. But there is a way to rescue it. There is something that is a Markov chain, and I want you to figure out what it is. All right? So I'm going to give you like 2 minutes to think, chat with your neighbors. How could you rescue this and make it into a Markov chain? As written, if this is the state, is not a Markov chain, we need to rescue it somehow. Okay, I'll give you 2 or 3 minutes to think, chat with your neighbors, and then we'll come back and chat as a class.
It's like, yeah, your state T is like rainy, sunny, or rainy, nice. Nice, rainy. And then you can go yeah, and you always, so if you're, it's rainy, no matter what.
Well, you define an initial state in the same way you would, which would be 2 days of initial state. Yeah, but then every forward state has the, like, the, will be the last. Each day will kind of be bracketed at the end and then start of the next one.
Okay, maybe people will stop talking because maybe we'll stop the timer 30 seconds early. So, I heard some people with some good ideas. Anyone want to say, how do you rescue it? How do you make it into a Markov chain? Yeah.
Do you have to specify what the initial state is?
So in a Markov chain, you can think of a Markov chain as this like machine that goes from one state to the next state.
Yeah.
That's like the link of the Markov chain, right? And we always, like if you really want to simulate it, you need an initial state.
Yeah.
So it's true, like you need an initial state if you want to run it, but I think you can sort of imagine the rules of the Markov chain without having to reference an initial state. And then like the initial state, someone will just tell us at the end. Like, so if you can kind of imagine the whole thing. By the way, this is why it's called a chain, right? It's like this little thing that gets you from one state to the next state is like the little machine that makes like a little chain, and then you like chain a whole bunch of them together, right? You go from one state to the next state, you go from one state to the state after that. It's like 2 links of a chain. I guess that's why they call it a chain. Mr. Markov was some Russian guy. I don't know. Okay. So yeah, that's like I think you shouldn't worry about if you're thinking about a Markov chain, you should only worry about the initial state, maybe at the end. Yeah.
Your current state is just like today's weather and yesterday's weather. So it's rainy, like I'll keep on going from there, yeah.
Okay, so this is a great, so the idea essentially is that the state should not be either rainy or nice. You're gonna have a bigger state space. How many things are in your state space?
4.
4. Why is it 4? How did you get 4?
2 to the 4. Sorry, 2 to the 2.
2 to the 2, yeah, because so basically so this one is not a Markov chain. That was a fact. But let's instead look at a new state space. New state space. Right? So this is like some completely different thing. And we're gonna make the states. Oh, we had a cool curly S for states. Can I do a curly S? Does that look like an S, or does that just look like some kind of like cobra? Okay, curly S. Okay, and it's gonna have 4 things in it. It's gonna have rainy, 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 nice, nice, rainy, and nice, nice. And what this state space is gonna encode is not just the weather on one day, but the weather on the last 2 days. So this is the weather on the last 2 days. And so now we have these like things. We'll have like ST will be rainy, rainy. And if ST is rainy, rainy, then let's make a new variable if we want. We'll make a new variable called weather, right? And the weather was what we were looking at before. That was not a Markov chain. We'll have like WT is rainy and WT minus 1 is rainy. So WT is the weather on day T, ST is the state on day T, and the point is the weather on its own is not a Markov chain, but if you glue multiple days of weather together to make a state in this like abstract state space, then it can be a Markov chain. Okay, and you do have to pick. There's one choice you have to make when you do this, which is what is the first letter and what is the second letter? So does rainy nice mean it's rainy today and nice yesterday, or does rainy nice mean it was nice today and rainy yesterday? You made it up, so you choose. Which one are we going to do?
It makes sense to go left to right.
Okay.
So I think the left should be like the current day, and the right should be the previous day.
Okay, so the left is the current day. This is the current day. And then this will be the previous day. Previous day. So no matter what you pick, half the class will hate you, unfortunately. So it really is just, I think you should, the way I think about it is like, there's little blocks, like wooden blocks with R and N labeled. And they arrive every day. We get a new block of like what the weather is, and then we're looking at the last two blocks. And then it's just a question of, are the blocks coming in from the left or are they coming in from the right? This like really just like is your worldview that blocks arrive from the ether. Do they come in from the right or from the left? And I guess you have chosen that they come in from the left, right? So the new blocks come from the left. They slide over all the old blocks, and then the current one is always the leftmost block. Other people, I guess, want to do it the other way. But you had your hand up first, so we're going to do it this way. Okay, so that's current day. So we're going to add that as an example. If ST is rainy, nice, then today is rainy, and yesterday was nice. Okay, and this one really is a Markov chain. If you know the state ST, that means you know the last 2 days of weather, and using the last 2 days of weather, you can figure out tomorrow's weather. There's one other important detail that when you go to write it down, you're going to figure out, which is that you also have to encode the rules of kind of like moving up by a day. I'll show you what that means. So this is the big transition matrix M. This is the transition matrix, the probability to go from one state to another state. Let's do +1, and we'll do S prime. Give it S, right? This is the transition matrix. And it's going to be a 4x4 matrix because we have 4 states. So we can label them as rainy, 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 nice, nice, rainy, and nice, nice on the rows. And then on the columns, we can do the same thing. Rainy, 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 nice, nice, rainy, and nice, nice. Okay. And so remember, in Markov chains, we decided that the rows are always where you come from. So the origin and the columns are always the destination, right? So for example, this first row over here is going to be, if you start on a rainy, rainy day, what is going to be the next day? And so rainy, rainy means today is rainy and yesterday was rainy. Here is the fact that is the thing I mentioned before. If today is rainy, then in the next state, yesterday will have been rainy, no matter what, which is a little bit of a confusing thing. That's because we're encoding 2 days of weather, and the weather that is today's weather today, which is the first thing, like R, that becomes yesterday's weather tomorrow. Okay, so this R is going to translate into this R over here, and that means that actually there is a big fat 0 in here and here. And there's a big fat 0 because there is no way to go from a state where it's rainy today to a state tomorrow where it was not rainy yesterday. That's completely impossible. And so these zeros are like automatically encoding the fact that if it was rainy today, this rainy will slide backwards by 1 and become the second rainy. We can also fill in the other two things by looking in what was given to us. So rainy, rainy. If it was rainy 2 days in a row, what happens? We can read that over here. It was in here. So if it's rained for the past 2 days, then it will rain again with probability 0.7. I know this is a little cut off for you. Let's try to fix that. Okay, so in here is probability 0.7, 0.7. So that would be rainy, rainy to rainy, rainy is 0.7. And on the other hand, I guess the rows have to sum to 1 still, so this one's going to be 0.3, which is if it was rainy, rainy, the next day will be nice, and then if the next day is nice, it's like nice, rainy, rainy, but we only keep track of the last 2, so it's like a nice, rainy state. Okay. let me know if you need more detail. If you're not following what's going on, I sound like a crazy person talking about nice rainy tomorrow, today, right? It just sounds like gibberish. So let me know. If it makes sense, I think it's okay. But please do let me know. Okay. Similarly, on the next one also starts with rainy. So again, it's going to have zeros here and here. There's no way to go from rainy today to nice yesterday. And we read off these two numbers from the instructions. If it rained today but not yesterday, that's rainy nice. Then it will rain with probability 0.5. So this one will be 0.5, 0.5, 0.5, 0.5. So then we've done the first two rows. In the next two rows, it's the same idea, but today is a nice day, which means tomorrow will definitely be something whose day before weather was nice, which means that there's zero chance to be here. So we kind of have this like blocky structure that happens. Okay, and what are the numbers? We'll read them off of the thing. Can I scroll down a bit? Can I zoom out a bit? Okay, I made it the font tiny, but we can read it. Okay, if it rained yesterday but not today, that's the state nice rainy, according to us, nice rainy. Then it will rain tomorrow with probability 0.4. So nice rainy, it'll rain tomorrow, that would be rainy nice. So that's probability 0.4. So yeah, so it's like nice rainy is today's weather, and then a rainy block comes over here, and then we read off the first two, so it's rainy nice. Okay. And because everything sums to 1, this has to be 0.6. And last but not least is if it has not rained for the past 2 days, that's nice nice, then it will rain tomorrow with probability 0.2. So that'll be the state rainy nice, 0.2, and 0.8. So we found the matrix, which is a 4x4 matrix. And this matrix encodes two things. It encodes the rules that were given to us here, and also the rules about how to slide over today's weather into yesterday, which is implicitly kind of hidden in all these zeros. All right, questions or comments about this example? All right, what is the moral of the story is that things that maybe don't look like they are a Markov chain, so the weather on the first day, like we saw over here, that is not a Markov chain. But you can make it into a Markov chain by just making the state space big enough that anything it depends on, just include that in your state space. Another example of this that I really like is chess technically is a Markov chain, right? If you know the state of chess, if someone gives you a chessboard, you might as well have played the whole game, right? It doesn't matter how you got to a certain state. If you know the state, you know you can play the whole game. But sometimes it's helpful to know how you got there, right? Because maybe if your opponent is doing some weird stuff with their king, you're like, well, they're maybe making a plan to like come over and kill me with their rook or something. And in the AlphaGo AI that played chess, they included, as a state, they didn't include just the current board, they included the board plus the last like 5 moves or something. So that the computer can take that as input and then predict what will happen based on not just what's happening now, but what's happening in the past as well. And so that can be helpful to make your state space bigger. Okay. Another great example is ChatGPT, right? ChatGPT tries to predict the next word. If ChatGPT only knew the current word and tried to predict the next word, it would suck. The current word is not enough information to predict the next word. You need to know all the words that came before, and in fact, a lot of research goes into making this window bigger and bigger. So can ChatGPT read an entire book and then output something about the book, or can it only read the last page of the book and then output something about the book, right? So an AI that can have a really large state space and read a huge amount of text and then use that to predict the next thing is more useful than one that can only read a small amount of text and then predict the next word. Okay. Okay, so that's enlarging the state space. Questions, comments? Okay, I'm going to set you loose on a problem like this, where it's not clear where is the Markov chain, but if you can make the Markov chain appear, then you can start to answer questions. Okay, and here is the problem. Here is the problem. It is about heads, tails versus heads, heads. Okay. So here is the setup. It's a little contest. And this question is the lightning mode question. So I'm going to read you the question. You're going to just like think, you'll be like, I don't know, I guess it's this one. We're going to see what you guys get lightning mode. Then I'll give you a version of the same question. We have heads, heads versus heads, tails, Markov. Well, I will let you think and write down a Markov chain. But let's see what our first intuition is, what's our instinct. So here's the game. Let's make it a bit bigger. Okay, here we go. So Alice and Bob are in a coin flip race. Alice is flipping coins, Bob is flipping coins. Alice flips coins until 2 heads in a row. So she flips, flips, flips. When she gets heads, heads, then she's done, she wins. Well, she only wins if she gets it before Bob. Bob is flipping his own coins. He flips until he gets heads, tails. All right, let n heads, heads be how many flips until Alice gets a heads, heads. It's a random variable. Could be 2 at minimum if she gets the first 2, or heads, heads 2. Could be 100 if she gets very unlucky and there's no heads, heads. Let n heads, tails be the number of coin flips it takes until Bob gets heads, tails. All right, so they're flipping coins. Here's the lightning round. Tell me, just thinking intuitively, no calculations, which is faster? Which takes longer on average? What's the average value of n heads, tails? What's the average value of n heads, heads? Which one is bigger? And of course, there's 3 options. One is bigger, the other is bigger, or they're equal. Tell me what you think. And this is lightning round, so you only have 30 seconds. You have 27 seconds. Just put in your intuitive guess, right? Okay, 7 seconds left. I think there's like one person who hasn't answered. Okay. Okay, we did a little jump there. Okay. Okay. So time is up. Let's see what people intuitively think. And again, this is not a calculation answer. This is just like, what do you feel? Okay. Okay. 3 people said Alice comes up sooner. 2 people said Bob comes up sooner. Right? So pretty split here. But the majority of people say they are equal. Of course, they should be equal, right? Like heads and tails are interchangeable, right? If you're waiting for heads, then tails, why should there be any difference? This is like what I would intuitively click on. And also, you see it's pretty split here. People who are like, wait a second, it's a trick question, right? Like, we wouldn't put it up there. They're pretty split. I'll tell you for a fact, this one is wrong. They do take different times. So congratulations to the 5 people who know that I'm very tricky. Sometimes I'm double tricky, though, so you got to watch out. Okay, anyway. So 5 people knew I was tricky, but which one is it? Which one is which? And the way you can solve this problem is by setting up a Markov chain, okay? So I'm going to let you guys think about this one, and I think you can come up to the right answer. So same exact setup as before, and to understand it, we're going to make a Markov chain. And we're going to make one Markov chain for Alice and one Markov chain for Bob. Both Markov chains have the same states, but they have different probabilities, okay? So you're going to think of what would be the Markov chain that kind of encodes this n heads, heads things, right? Like, we have looked at Markov chains in the past, where we're counting the number of times until something happens. The number of times until you hit 9 on snakes and ladders, the number of times until the drunkard gets to either end the police station or home. So n heads, heads is some kind of thing like that. If you set up the right Markov chain, these n's are like how many steps until you escape the Markov chain thing. And I give you a hint, there's a Markov chain with 3 states. So even less than our weather model. It's kind of simpler than our weather model. There's 3 states for each of them. And if you write down the probabilities, you will figure out who is faster, Alice or Bob, and you'll see why they're different. Okay, that's my hint. I will give you 2 or 3 minutes to think, talk to your neighbors, see if you can write down the Markov chain, and then answer the question. And don't select they're equal. They're not equal. Okay.
But then you go from tails to tails to, are there no 4 states?
So it's possible to set it up with 3.
Okay.
If you set one up with 4, that's also possible, I think. If you have one with 4, there's probably a way you can simplify it down to 3.
Okay.
Okay, so there's like 15 seconds left. Most people haven't answered. I'll give you guys a little more time. But maybe, has anybody figured out what the 3 states are? Well, we could write down what the 3 states are without completely giving it away, right? Has anyone figured out a good way to think of what are the 3 states? Yeah, at the back.
Of course, we have the heads, and the heads, tails. But
Okay.
if you hit a tails, it doesn't matter what you get next, so tails is just tails.
So there's heads is one state. This is what you're calling state number 1.
Yeah.
Okay, what's the next state?
Then heads, tails, and then tails, X.
Is tails.
X.
I'll put tails question mark.
Yeah.
So it could be, the question mark could either be tails or heads. Yeah, X is another good way to describe it. Okay, and heads, tails. So again, same thing as the rainy sunny. Which one is the most recent coin flip? Is it the one on the left or the one on the right for you? Like to interpret this heads, and heads, tails. What's the most recent one?
The most recent one is the one on the right.
On the right. So the one on the right, so that would mean I just flipped the tails, and this one would mean I just flipped the question mark? Is that what you want? Or do you want the other way around? So here's a good way to do it.
The other way.
The other way, okay, good. So I think this one is the most recent.
Yeah.
This is the most recent. This is the most recent. And so, for example, if some sequence of coin flips comes out like tails, 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 heads, tails, then I look at the last 2. And this, so okay, yeah. So this is, again, this is like one of the only ways you can screw it up is going left to right or right. So here I wrote them like this. I wrote like this is the most recent. This is like coin flip 0, coin flip 1, coin flip 2, coin flip 3. And then if you look at the last 2, that's coin flip 4 and coin flip 5. But the most recent one is tails, right? So this is actually this tails question mark. So just be careful of that. If you're writing out the coin flips as they occur from left to right, then it will be backwards to what is here. So this thing is really this thing. This thing and this thing are the same because the most recent is tails. So just be aware of that. One way to fix it is you can write question mark tails, but you just have to write. You have to just be like consistent with yourself and like know what you mean and explain it the right way. So just watch out for that. But these are totally 3 valid states. If you use those 3 states, you can write down the Markov chain for Alice, write down the Markov chain for Bob, and it should be like quote unquote obvious. I mean, it's not obvious, but it should be easy to see who is faster, who is going to get to their target first, on average. So one of them is going to have an easier time getting to their target. One of them is going to have a harder time. Okay, let's see. How many answers am I up to? I'm up to 14 answers. So maybe I'll give like 10 more seconds, 15 seconds for the last couple people. And then we'll look and see if there's a consensus. And if there's no consensus, we can go through it. Yeah.
Oh wait, I was thinking my question was wrong.
Okay. Okay, well, let's see what people said. So time's up. Let's take a look here at the counts. Okay. So, great. Everybody was awake. Very good. 13 people thinks Bob comes up sooner. So heads takes longer than heads tails, which means Alice takes longer than Bob. So Bob is coming up sooner. 5 people think the opposite. It's a pretty good split. Let's see the right answer. Very good job. So most people got it. And the way you can see it is by just looking at the Markov chains. You can sort of see that one of them kind of has this like save state thing going on. And one of them you have to start all the way over. And that is what's going on. I could explain it to you, but fortunately there's a very nice YouTube video for this problem made by a very nice person. So I thought I'd just use that instead. So here is my like 2-minute version of this that has been pre-recorded and made. Will the interesting parts of the screen be cut off? We'll find out. Okay, is this loud enough? Towards the target sequence. For the sequence heads tails, you either have no progress, for example when the last coin flip that came up was a tails,
Or you are halfway towards heads tails when the last coin flip was a heads. Or you have finally reached heads tails itself. We can think of these as abstract states of how much progress we have so far. Heads heads has completely analogous states. The only difference
so
between
these are-
heads tails and heads heads is going to be found in the details.
This is exactly the same as the states you guys wrote down. The only thing that is new is I have labeled them with the amount of progress, which is either 0 progress. If you end in a tails, you have no progress. You need 2 more coin flips to get your sequence, or 1 out of 2 or 2 out of 2 when you're done. So I just took exactly what you guys said. This is like tails question mark. It is backwards, right? I wrote it as question mark tails, not as tails question mark. So it's good to know. But it literally is exactly the same thing as before. Okay, let's keep watching and see.
Of how we move around between these partial progress states. Starting from no progress, you have a 50% chance to flip a heads and move to the 1 out of 2 progress on the next flip. You have a 50% chance to flip a tails and stay at the 0 out of 2 progress state. This is identical for both.
Okay, so you can't quite see it. The arrow goes back and comes out in the side of the tails. Hopefully that's okay. It's a little cut off.
Both heads heads and for heads tails. Similarly, starting from the halfway point, both sequences have a 50% chance to finish on the next flip. The only difference between the 2 sequences is what happens when you are at the 1 out of 2 state and you miss your next coin flip. For heads tails, since missing means flipping another heads, you stay where you are at the 1 out of 2 state. You can think of this as a checkpoint where your progress is saved halfway towards heads tails. On the other hand, for heads heads, if you miss, that means you must have flipped a tails, and you have to go all the way back to the 0 out of 2 state. You now have to start all over and flip a heads again before you can progress. Clearly, it's going to be faster when your progress gets saved halfway. So by comparing these graphs, we can easily see that heads tails should indeed be faster than heads heads.
Okay. So that's the picture of the Markov chain. Question here, yeah.
Is that your video?
That's my video, yeah. That was the joke. Okay. Yeah, I will say, you guys, we have seen like 1 minute of this video. Why is the video 20 minutes long? There's some other crazy technique to get the expected number for both of them using something called martingales. It is very tricky, and you can get the number. So that's what the rest of the video is. I think, okay, actually, maybe I'll say that in the video.
However, it's not at all easy to see how this chart would produce the numbers 4 and 6 for the expected number of coin flips.
In the video, this one takes 4 flips on average, and this one takes 6 flips on average. So you guys were right, this one takes longer, but why 4 and 6? Okay, there's a tricky way to do it. Of course, you guys have taken a class on Markov chains now. How can you get 4 and 6? You set up the matrix, you do the things to get the expected number of steps, and it will come out 4 and 6. So if you take the matrix for both of these, right now it's written sort of as a graph, right, where you go to where you go. You can convert that into a 3x3 matrix. And then if, just like on lab 1, you answer the question, given the 3x3 matrix, how long does it take until you reach the final state, you'll get 4 and 6. But there's a tricky way you can get 4 and 6. I won't go into the tricky way. If you want, you can see the video on your own. I'll post the link. Okay. But yeah, most people got that. Other questions or comments? Yeah.
When you're first flipping the coin, isn't
Yes.
there 50%, like you have a 50% chance to end up in the tails state,
Right. Yeah.
But then you have a 25% chance to end up in the head tails or head head, right?
Well, we look only 1 coin flip at a time.
Okay.
So it's true that when you this is a good point. Where do you start in this thing? So I wrote ... tails, but in your very first flip you really have nothing, right? There's no, you have no coin flips. You flip the first coin flip. Where do you start? Well, that's why I think you should think of it as 0 out of 2. When you start with nothing, you have no progress towards your sequence. If Alice is looking for heads heads, that's like she needs 2 coins of progress. So she starts with nothing. You could start with nothing by being on something that ends in tails, or you could start with nothing because you literally have no coin flips. Either way, you start at the 0 out of 2 flip. And you're thinking about things like what happens 2 flips from now, right? And indeed, there is a 25% chance you can get to heads heads in 2 flips. If you go 50% and then 50%, she would be getting to 2 flips and immediately 2 coins. There's also a 50% chance and a 50% chance of heads tails finishing in 2, right? So 50-50. So in 2 coin flips, they can get to finish. That's both 25% for both of them. But on average, it takes longer for heads heads because there's all sorts of other things that can happen, right? And I think the key is, in a Markov chain, you want to break down into the smallest possible thing that matters. And that's 1 coin flip at a time. So if you think about this problem as 2 coin flips at a time, 25% chance of winning, then it's very hard to analyze. But if you think about it one coin flip at a time, then you see what the difference is, right? When they go one coin flip at a time, they have to go through this 1 out of 2 state, and that's where the difference is. So the heads people, they get restarted a lot of the time, whereas the heads tails people, they get to like checkpoint their progress here. Okay, yeah, great question. Any other? Yeah.
This reminded me of some stuff I learned in like a computer science course. Is there such thing as a non-deterministic Markov chain where you can be in multiple states at once?
Oh, okay, that is a fantastic question. So again, the answer, like very technically, is no, because like the state is defined as a thing, and like if you know the state, you're supposed to automatically, like the definition of the Markov property is if you know state at time t, then you can figure out the state at time t plus 1. So
Okay,
like,
so it's deterministic.
well, it's random in that you know the probability to go.
Yeah.
But so like technically speaking, the answer is no. But like informally speaking, the answer is yes, because you can make a Markov chain where the state includes all sorts of like weird things.
Okay.
So like you shouldn't think of the state as just the weather on today. The state could be the weather on today plus what is the pressure in Bermuda plus like what is like the state could include all sorts of crazy stuff. And as long as the state, whatever it is, whatever abstract thing the state is, as long as that includes enough information to figure out what are the chances of the next thing happening, then it's a Markov chain.
Okay.
So yeah, so the answer to the question is you have to make the state big enough to matter. And this is a great example of some real life problem about coin flips that we like made these states and they answered our question for us. Okay. Other questions or comments? Okay, so that is it for these like funny examples of Markov chains of how, like you can use Markov chains for all sorts of things because you can always like make the state space whatever you want, and then you can figure out things like this. So you can do all sorts of cool things like that. That's what I wanted to show you today. The other thing that I was going to show you is about the Bellman equation, which is where we left off on Tuesday's class and is related a little bit to question 3. So I'm going to prove the Bellman equation for you now, and we're going to talk a little bit more about that. And that's going to lead us into reinforcement learning, where we're going to have a bigger version of the Bellman equation that includes actions as well. So the one we're doing, I really call it the Baby Bellman equation because it's only for Markov chains. When we do it for Markov chains with actions, that'll be the real Bellman equation. Okay, so let's transition, switch gears a little bit, and do this topic. Okay, so I want the Bellman equation, and I'm doing what I call the Baby Bellman equation. Okay, and so the Baby Bellman equation was for this thing called the value function. So the value function is a function that inputs what state you're in, and it is defined to be the expected value of the total return. That was called G0, given S0 equals lowercase s. So it's a function, you tell me what state you're in, and I tell you what is the total expected value of the return given you there. And this is a confusing thing. You have to know the difference between return and reward. So a reward is like something you get on your way, and the total return is the total amount you get at the end. So we had this formula that GT is equal to the rewards at time t plus the rewards at time t plus 1 plus the rewards at time t plus 2, and so on. Okay. And in principle, it can go up to infinity. In practice, we look mostly at Markov chains that eventually end. So like snakes and ladders, with 100% chance you will get to the end, and then at the end you stop getting rewards. So we assume that we don't worry about the issue of convergence of GT. We say it's like finite, almost surely. With 100% chance, it's a finite number. Questions or comments? This was all review from Tuesday. I know that was a long time ago, though. So questions or comments? Okay, there is one thing that sometimes appears, and I'm going to include it just now. So if you see it somewhere, you don't think it's crazy. Sometimes people put in a factor of gamma. So they do GT instead of being RT plus 1, they put in gamma, and then they put in a gamma squared, and then they put in a gamma cubed, and so on. Gamma is called the future discount factor. Or the discounting rate. If you know like finance type things, this is a common idea in finance that $1 a year from now is worth less than $1 today. How much less? Well, gamma. And that kind of discounts all the future rewards so that we count rewards today more than we count rewards there. So this is some number in 0, 1. If it's exactly equal to 1, then all the rewards count equally. And I'm not going to write gammas after right now, because they're just kind of annoying. They don't actually add a lot. But just so you know, if you see a gamma, don't panic. We're always doing gamma equals 1 for simplicity here. Okay. So that is the value function and the rewards. And the Bellman equation, or the Baby Bellman equation, it said this. It said that this was the equation that we derived, that the value function is equal to the expected value of the rewards, let's say v of s. The rewards, let's say at time 1, given s0 equals s. So how much value do you have? That's how much money you're going to get forever and ever, or not money. How many rewards you're going to get all the way up to time infinity. And the value function is equal to the rewards you get now. So the rewards at time 1 when you start there, plus something else. And that something else is where the transition matrix comes in. I'll write this thing as m times v of s. And by this I mean you apply the transition matrix m, you think of v as a column vector, you apply m to v, and then you take the s entry of that. So as a vector, this is v equals r plus m s, where r is rewards, the reward vector. And so, for example, if you get a reward of -1 at every state, then the reward vector will have a lot of -1s in it. Any state where you get a -1, the reward vector will have a -1. Okay, so that was, I claimed that last time, I didn't prove it. And we're going to prove it now and go over some details of it. But any questions or comments with the setup? Yeah?
What's the vector s here? Sorry.
Vector s. There shouldn't be a vector s. Where is it? Oh, this thing?
Just below it. M
Ah,
multiplying s.
yes, okay, very good. This is me making a mistake. It should say mv. Okay, very good, thank you. Yeah. This is a good way, a good use of writing vector signs on things is then you know if you made a mistake. Thank you. Yeah.
Maybe I'm mistaken, but don't we usually multiply the vectors on the right of the matrix?
Yeah, this is a fantastic, this is what question 3 is all about on your lab. Okay, so in the course so far, I've done a lot of matrix multiplication with the matrix M. This transition matrix was like the boss, right? Like if you know the transition matrix, you own the Markov chain, you can do anything you want to it. And in the past, we had this equation. We had equations like P of t plus 1 equals pt times m. And when you're doing probabilities, you multiply on the left. That makes perfect sense. Probabilities multiply on the left because every row sums to 1. And so if the pt was a probability vector where all the entries sum to 1, then pt plus 1 will also sum to 1. Everything makes sense. Probabilities multiply on the left, but values multiply on the right. So things like rewards, prizes, stuff like that will multiply on the right. And one way you can think about it, yeah, this is exactly what question 3 on the lab was supposed to get you guys to work on and figure out. But one example, let's do one example. What happens if you do m of 1, 1, 1, 1, 1, 1, 1? Okay. So m of 1, 1, 1, 1, 1 is going to represent, I am going to give you a reward of 1 no matter where you are in the Markov chain. So you can think of this 1 as some kind of prize or reward of, I'm going to give you 1 prize, 1 toy candy, and I'm going to give it to you no matter what state you're in. So wherever you end up, you will get a prize candy. M of 1, 1, 1, 1, 1 represents the vector whose entry is, starting here, how many candies am I going to get after one step? And in principle, it could be less than 1, right? Because maybe I step somewhere where I get 0 candies. But M of 1, 1, 1, 1, 1, if you're going to get a candy anywhere you go, then how much value do I have? How many candies am I expected to get now? It's 1 no matter where you are. Because no matter where you step, you're going to get 1 candy. And M of 1, 1, 1, 1, 1, you can check, we've done this one before, is still 1, 1, 1, 1, 1. So this is M of 1, 1, 1 represents 1 candy, 1 candy per state, maybe I shouldn't say per state. I'll say in each state, and let me add a power t. So m to the power t, we'll do t steps from now. So m to the power t of 1, 1, 1, 1, 1 represents, I'm gonna give you 1 candy in every single state, and I'm gonna look t states from now. Where do you end up t states from now? And the reason it's 1, 1, 1, 1 is because the expected number of candies you get is always 1. Expected candies is always 1. So candies after t steps. Okay, so this is like a dopey example, but maybe it can help you understand. And yeah, question 3 is all about this idea of what does matrix multiplication on the right mean. Okay. Yeah, so it's a great question. Any other questions or comments? We're going to see when I derive it, you'll also see where it comes from. But yeah, question here? Yeah.
Yes. Why is it 1, 1, 1, 1, 1 after t steps? Is it that you get a candy each of the t steps, or only at the final?
Only at the end. Yes, that's right. Yeah. So this is a great point. Is in the Bellman equation, the reward vector is some other vector over here, and that's like what you get every step. And if you do just powers of m, then it's like the prize thing, or like what you get at the end.
Can I see what's on the right side there?
Yes, I can try to fix this a bit. It says, expected candies after t steps. Although it doesn't really look like that. Oh, I spelled candies K with an I-E-S. I don't know if that's right. What's the plural of candies?
Like that.
I'm saying candies now, and it does not sound like correct English. I'm going to blame it on my foreign parents. They told me candies. I guarantee my dad says candies. So we're going to count that. Okay. Whatever, it doesn't matter. Okay, things. I need to move on. Okay. All right. Other questions or comments? But we're gonna prove the equation, and you're gonna see where this matrix multiplication comes from, kind of like very specifically. Okay. Stop me now. I'm about to do a proof. It's like you have to stop me now if you have questions. Okay, let's go. Let's do the proof. Okay. So this is we're gonna divide all the rewards, right? All our return GT. We're gonna look at G0. G0. Which is the rewards you get now, plus the rewards you get tomorrow, plus the rewards you get the day after, and so on. That's GT. And we're going to do something that sounds so dumb, but is a true fact about the universe. You can divide up the universe into 2 things. The things that happen now, and the things that happen after now. I also think I'm off by 1. I think the way everything is written, this starts at 1. Let me just erase this one. Okay, so we're going to divide this into 2. The rewards now, and then everything else is going to be rewards after now. Rewards after now. Okay? And this turns out to be a useful way to think about it. So the total value you get, the value function, when you're thinking about the value function, which is what we're looking at, right? Which is the expected amount of value you get. The expected amount of G0. G0 given S0 equals S. So if you want to look at the total amount of value you have, well, I'm going to get some value now, and then I'm going to go somewhere, and I'm going to get some amount of value from that spot. And I'm thinking about this division as a division into 2 pieces, and that's going to make us derive our equation. And in fact, I'll give you a spoiler because you know the equation. The equation has the 2 pieces. So the value vector is going to be 2 pieces. It's the rewards you get now plus the rewards you get later. And we're going to see that the rewards you get later is MV. Okay. So, and there's a very nice mathematical way you can do this. You can notice that R2 plus R3, this tail of the sequence, G0 is the sum of everything. This tail of the sequence is G1. So this is actually G1. Let me write it like this. So this is going to be R1 plus G1. So the rewards you get at time 0, the total return you get at time 0, all the stuff you get some stuff now, and then you get some stuff after 1 step. And so when I do the value function, which is the expected value of G0 given S0 equals S, this will be split into 2 parts. There's going to be the rewards you get now, plus the return you get starting at state S0 equals S. So I'm just using linearity of expectation to split it up like that. The total rewards you get is R1 plus G1, R1 plus G1. I just split the expected value apart. And this one is exactly the reward vector, right? So this is starting at state S. How much reward do you get in the next step? That is what we called R. Or more specifically, it's R of S. R of S, right? So R is the vector with all the things, and here I put in the state S. This one, I claim now, is going to be a matrix multiplication by the transition vector. Why is it a matrix multiplication by the transition vector? Well, the transition matrix M moves you from state 0 to state 1. And this is exactly what we're doing here. We started at state 0 equals S, and we're looking at something at time 1 that's exactly moving forward in time by one step. So it's not surprising that the matrix M is going to appear here. But let's see like why specifically. And I'm going to write this out on its own. So the expected value of G1 given S0 equals S. I'm going to write it exactly using the law of total probability and conditioning. So this is like, to get a formal proof of this stuff, you can write out things and use the Markov chain property. That's what we're going to do. So I'm going to do the expected value of G1. Instead of being given that S0 equals S, I'm going to be given that S1 equals S prime and S0 equals S. And then I'm going to multiply by the probability. Okay, let me do it on the next line. So we're going to do a little multiplication times the probability that S1 equals S prime given S0 equals S. So this is the law of total probability. So it says if you want to know the expected value of something or the probability of something, you can divide it up into all the possible things that could have happened and look at each of those cases individually. And if you add them up, you'll get the total value. So this is actually the sum over all S prime. So the sum over all states. Okay, so I want to know what's the probability of the probability of the expected value of this thing happening. I split it up into all the possible places you could be, and I call those states S prime, and I sum over all of them with the correct probabilities. Okay. Now there is a nice thing that happens, which is the Markov property. And the Markov property lets you simplify this a bit. So very technically speaking, in the law of total probability, you are given two things. You're given that you're in state S prime at time 1, and that you're in state S at time 0, right? So for some arbitrary process, you can always do this. You're going to have this two thing given where things are at time 1 and where things are at time 0. But here is the fact about Markov chains. If you know where you are at time 1, where you were at time 0, completely irrelevant, right? That's the whole point of a Markov chain, is that if you know S prime, then this fact that you were at S, whoever, like ages ago, completely irrelevant. It won't change anything going forward. The only thing that matters is this S prime. So by the Markov property, we can just delete this bit. That's by the Markov property. And this is why it's important. It's a Markov chain. Otherwise, this thing won't work. So if you want to know, in a Markov chain, if you want to know the value you get in the future, then you only need to know about the transition matrix M. In an arbitrary process that is not Markov, then it's not going to work. Okay. So by the Markov property, you might as well just delete that. I could write it all out again and leave it off, but I think this is more exciting and illustrative. Yeah, question?
Is that why wouldn't it also work in the probability of state 1?
Okay, yeah. Well, so in this one, like in this probability, we're only conditioning on state 0 and state 1. And the Markov property says if you know what it is today, you can delete all the information about the past. That's irrelevant. But this one, there's nothing like we could delete anything behind S0 here, but there's nothing behind S0 here. So we can't just delete this one. Yeah, that's a good point. So like the reason we can delete this one is because this one is here, and the Markov property says this one is so much more important than that one's irrelevant. And this one, in the probability, there's no like something after. Yeah, so it's a good point. Any other? Yeah.
Does this mean you combine that S0 property into this dual property that we did in the medium class, or?
Yeah. So this is why whenever you're making states, the states you want them to have the Markov property, so that you can do this kind of thing. You can use all the equations. So that's why if somebody gives you this like weather problem, or you're looking at the last 2 days, do not make the states the weather on the teeth day. Do not make ST the weather on the teeth day. Make the state something that obeys the Markov property. If the state is something that obeys the Markov property, then you can do these like cross-offs and things will work nicely. Yeah. Same idea with the coin flips. Okay. Other questions or comments? So if you look at the sum, you should recognize there's going to be an M somewhere, there's going to be a V somewhere, and it's going to be exactly a matrix multiplication. So if you see that, that's exactly what we're going to do. But let's stare at this for a bit and see where is the M. Well, M is the matrix that tells you what's the probability you go somewhere given where you are now. That's exactly this probability. So I could write this thing. I could rewrite this whole sum as the sum over S prime in S. Okay, my S somehow turned into a C. How do I do an S? I guess it's like this. Okay, there we go. S. This probability over here, this thing, is exactly the matrix. That's the matrix. M, let's do a blue underline and we'll call it M of, and okay, this is the thing, right? Is it M S S prime or is it M S prime S? This is like important. And we chose, I don't know who did this, the probability gods chose this, that you always put the place you are coming from as the row and you put the place you are going to as the vector. So the row, this is the row, this is from, and this is the column, this is to. So in this situation, we are coming from state S, we are going into state S prime. So this is M sub S S prime entry of the matrix in row S, column S prime. That's exactly that thing. All right. So that's how the matrix appears. Any questions about how that works? The matrix is exactly this probability. Okay. What about this one? Let's look at this one. This one, let's write it out one more time. So it's the expected value of G1 given S1 equals S prime. Yeah, okay. That is very close to something earlier. Oh no, I've made a very unfortunate typo. No, I haven't. Okay, no, we're good. Okay. This should remind you of something that happened earlier. So what is this one like? What is this one like? And I will, as a hint, I will zoom out a bit and scroll up until it appears again. Okay. So what does this one remind you of? Yeah.
R of S prime?
It's R of, very close, yes. So it has something to do, right? It's something to do with like how much value you have starting from state S prime. And R is also something to do with how much value you get starting in state S prime. R is the rewards you get immediately. So if I replaced G with an R, then you would be exactly right. But it's a G, and G, remember, is the returns, not the reward. So what is the difference? G includes everything into the future, forever. Yeah?
Is it V of S prime?
Is it V of, let's look. So I have a formula for V of S prime. The formula for V of S was this, and it was saying starting at state 0, how much returns do you get in the future? And this is saying starting at state 1, at time 1 at S prime, how much do you get in the future? So this is this question mark? Is this the same as V of S prime? And the only possible difference is that this one has a 1, and the definition of V had a 0. Okay? But again, because of the Markov property, they are exactly the same, right? So the Markov property, we're looking all the way into the infinite future, starting at state S. And we're saying, look, starting at time, we're going to call now times 0. How much value do you get all the way into the future, starting at state S? And this one is exactly the same thing. We're just like labeling it differently. We're like, wherever you are, at time 1, G1 is the sum starting now all the way into the future. How much value do you get starting at state S prime? It's exactly S prime. So yes, it is. And again, so there's a fact that there's sort of a time homogeneous component here, right? Like the only thing that matters is where you are. It doesn't matter what the clock is, right? In Snakes and Ladders, it doesn't matter if it took you 4 turns to get to state 5 or if it took you 3 turns to get to state 5. The number of turns left until you finish the game is going to be the same either way. Okay. So this really is V of S prime. Okay, so let me write it like this. V of S prime. And altogether, this is a sum. It's the sum S prime in S, and it's V of S prime times M of S prime. And you should recognize this as matrix multiplication. And here it's very important that I got the row and the column right, because this is matrix column vector multiplication. The row of the matrix is fixed, and I'm summing over the column, so I'm going down. Yeah. Did I get it wrong? What's going on here? From S to S prime. The row, and then you want to know the row. Yeah, okay, so So yeah, this I claim is equal to, okay, I'm not going to try to explain it because I think I'm just going to confuse people more. This is equal to m times vector v, and then you take the sth entry. Okay, and you're summing, you move which column you're in changes by the dummy variable s prime. If you want to think about s prime, you could think about it as going from 0 to n. That's how we've done all the examples in the course. We've always labeled them 0 to n, and then it really is moving across the matrix M, going from column 0, column 1, column 2, column 3, column 4. You're moving across the row S, and you're adding up as you go. That's exactly matrix vector multiplication. Okay, that's the proof. Questions or comments? All right, so what is the moral of the story? Is the matrix M, if you apply it to value vectors, it moves things forward in time by one step, right? So the expected value of G1 given something is M applied to what it is to G0. And this works for a lot of different things. Any kind of like value function you have will obey this thing moving forward in time. So altogether, so combined, we get the Bellman equation. And I'll say it's the Baby Bellman. We'll see the real Bellman next class. Okay. Any questions or comments overall? All right, now I'm going to give you a problem that's like a deja vu problem, right? We got this Bellman equation. I said the value function must satisfy the Bellman equation. But this does leave a question, which is, yes, it satisfies the Bellman equation. Some people call this a necessary condition, but is it a sufficient condition? In other words, if you solve the Bellman equation, did you get the value function? Does it go both ways? And I phrased this problem like this. Okay, and I made a specific example. So the Drunkard's walk, that was the practice problem. So it's on the state 0 to n. 0 and n are absorbing states, right? Which are the police station and the house. And you want to know how long until the Drunkard reaches either the house or the police station. This was one of the example problems. So this is the reward vector that looks like this. It's the reward vector, which is a 0 at the house and a 0 at the police station and a -1 for all the states in between. That means every time you take a step, you gain, you lose one time reward, so we will count the whole thing. So the Bellman equation is v equals r plus mv. That's what we said. And here's the question. Does solving the Bellman equation give you the value function? So if you just take the Bellman equation, v equals r plus mv, r is that specific vector, m is the transition matrix. You put it in the computer, you say solve, will you get the answer? And I made some options. So yes. And then there's no, you need one more equation, no, you need two more equations, or no, you need three more equations. And I want you to think about which. So I'll give you 2 minutes. Chat with your neighbors.
Solving this will pin down v precisely. Holy jeez Louise. I think so because, but it might be, I just don't really sure it doesn't. Because it's a vector, it includes all of the starting positions, like it takes that into account. So that would just pin down like one of the entries of it, but that it does a solid team. I'm happy, I was happy with it.
Yeah, put in an answer, but I didn't.
You're right, we'll need one other one because there are two absorbing states in the equation. So that's what I'm gonna guess.
That was my best guess.
Okay, there's like 20 seconds left. Put in your guess if you're not sure. It's okay to guess.
That's my best guess.
Okay, I think we have Everybody is. Okay. Okay. Let's stop a little early here. Okay. Okay. So 7 people said yes, just solve it. That means 14 people said no. Turns out the answer is no. So if you said yes, unfortunately you're wrong. Why do you need more? It is very similar to when we solved the equation for the steady state probability, right? That was also an equation of the form P equals, and it was the other kind of multiplication. It was P equals PM. And in both of these situations, because M has an eigenvalue of 1, there is some ambiguity, right? You cannot just solve the equation. There is no unique solution. There's infinitely many solutions. They make a whole space. That thing is related to the eigenspace of eigenvalue 1. And in this situation, it's the right eigenvectors. In the probabilities, it was the left eigenvectors. But anyway, the correct answer is no. Last time we did it, it's true there was only one equation. This time, there are how many? There are 2. You need 2 more equations. Does anyone know what the other 2 are? I will give hints, but let's see if anyone wants to say. Yeah.
Is it like the snakes and ladders one where we need the each state that is a end state is set equal to 0?
It is exactly like that. So the reason there are 2 equations here is because there are 2 end states, and we need to specify that we want v to be 0 at either end state. So let me write this down. So combine to get the Baby Bellman equation, and this is a note about solving to get the value function. And you must include information about the end states. Okay, and the example I'm going to give is in the Drunkard's Walk. So if you solve v equals r plus mv, and then you also include that v of 0 equals 0 and v of n equals 0. Which, by the way, these you could write these equations as v dot product something, right? You could write this as the vector 1, 0, 0, 0, 0, 0 dot product v. That's equal to v0, and you could write this other equation as 0, 0, 0, 0, 1 dot product v. That's the vn. You need to specify these are 0 if you want to get the amount of time. And really what you should think is this equation in the middle is telling you the information that every time you take a step in the middle, your clock goes up by 1. Right? That's really what we've specified here. The reward vectors are exactly doing that. The reward vectors are this thing. Okay, they're with minuses. -1, -1, dot, dot, dot. -1, 0. It's saying every time you take a step in these middle states, we tack on a -1 to your reward. And these are saying, okay, if you're at the police station or the house, you are done, and it's over, no more rewards. And without this information, there is no unique solution. So for example, here is another solution. Example, an alternative solution, is what if I added 10 to everything? If you take this solution and you add 10 to everything, you add 10 to every single component, it will still satisfy the Bellman equation. So if you add 10 to every component, that's adding 10 times the vector 1, 1, 1, 1, 1. On the left-hand side, you've added 1, 1, 1, 1, 1. On the right-hand side, you've added m times 1, 1, 1, 1, 1. And m times 1, 1, 1, 1, 1 is, again, 1, 1, 1, 1, 1. So this equation is only accounting for the differences. You need to anchor it to reality by including some endpoints. And I have another example of that for you guys to do in the last 8 minutes here, which is exercise 5. Okay, so here is the Drunkard's Walk, but with rewards. So this is like one of those drunkards guys, but he tracks his time and his he has like a calendar where he tracks everything meticulously, and he says, I'm going to give myself a -1 for every step I take. I get like -1 point for every step I take. If I get home, I get a +5. Okay? So if I get home, that's like a +5. So if I can get home in less than 5 steps, that's like an overall win for me. If I get to the police station, I get minus 100. So the police will like drive me home or whatever, but like it's sad for me. It was minus 100. And the question is, so you got to think of these as like abstract life points or something, right? Like before, it was the reward was the amount of time, because the only way to get a reward was by steps. But now the rewards are some like vague thing, right? Like they're like -1 per step, +5 if you get home, -100 if you get to the police station. You can think about it like a video game. It's like the score or something, okay? So here is the equations you would have to solve for this. And again, there's going to be two equations. There's going to be the Bellman equation. You got to tell me what R is. How did R change? So the Bellman equation with R, I put in the -1s, but I left these ones blank for you to fill in. And then I put in two boundary conditions, which are what is going on at state 0, what is going on at state n. You need to specify those as well. And if you get this all set up, you'll have a perfectly good equation that solves what you want. But I want you to think of what are the rewards and what are the endpoint values. Okay, and I'll give you, again, let's say 2 or 3 minutes to do that, and then we'll have just enough time to dig it up.
Yeah, that's a good point. I definitely agree with these, that's for sure. It's just, no pressure, and still zeros. Let's remember like okay, but because it started with B, and we know that in the new situation of the 5 is an angle of 100, that means that it does have to, I think it means that they do have to be -100 and 5. What?
Okay, there's like 10 seconds left. About half the people haven't answered. I'll give another 30 seconds, but put in your guesses here.
Right, because those are separate.
Or would we be double counting it?
That's what I'm thinking, is if this isn't 0, then it's confused. Yeah, I agree with this.
Okay, 10 seconds left for the last two people. Okay. All right, let's take a look. So you have these numbers that we know are relevant. They are +5 and -100. I've already included all the -1s in the reward, right? So the question is just like, where do they go? Do you put the +5, do you put it in the reward vector, or do you put it in the end? Where do you put them? And let's see what people said. Okay, so which one am I looking at? So the reward vector is the one with all -1s. Let's see. 5 people put in 0. 2 people put in 5. And 12 people put in -100. If it was going to be 5 or -100, then you would put the -100 over here, because that's the police station. And you would put the 5 over here, which that seems like what most people did. However, the correct answer is that you put in 0. You should put in a 0 here. These rewards, when you have the reward vector, those are the ongoing rewards. Those are the rewards you get at every state. And you can if you like squint your eyes and stare at the Bellman equation is sort of this dynamic thing that tells you what's going on every single term. So if it's in the Bellman equation with an R, that is an ongoing reward that you get every single turn. And these ones, in fact, have to be 0, otherwise there's going to be some kind of like infinity going on, right? If you had a non-zero number here, the only solution to this would be like something with infinities, because once he gets home, he would like get a reward like every step, right? He'd just be like, I'm at home, I'm at home, I'm at home. I'm getting like a cookie every minute for the rest of eternity. You have to put in zeros in the terminal states for the rewards, or everything will explode. Okay, so these in the rewards has to be zeros. Inside the boundary condition, that is where you put in the minus 100 and the 5, and that is representing the fact that we want the expected reward to be minus 105 at the end. So remember, the value function v of s is supposed to represent the expected value of the total prizes, okay, I'll call it total stuff. And stuff has two things, right? Rewards plus prizes. And I'll use prizes to mean one-time prizes. V of s is like the total return. This total stuff is called the return, total return. Right? And you can get rewards on the way at these states where you can like continually get rewards over and over again every turn. That's the R vector. And the prizes are kind of what you get at the end. And that's given s0 equals lowercase s. And if you just stare at this equation, if you're in a terminal state, so v of some terminal state, then the rewards are 0. Rewards are 0. And so what you get is just however many prizes are in that reward. Okay, this is equal to the expected value of the prizes at that state. Terminal state. Okay, I put some dots because I got close to the end thing. Hopefully it's okay. Yeah, it's off the screen anyway, so it's fine. Okay, that says terminal state. Okay. This is just like problem 3 in your lab. So the point of problem 3 was to get you to think about this organically. You basically know, if you have been paying attention here, the last little bit here will solve problem 3 for you. If the prize is either 0 or 1, the expected value of the prizes is something that has a nice interpretation. That's problem 3b. In problem 3d, the bonus, the hint is there will be a Bellman equation for something. The reward vector, you got to figure out what it is. It's going to be something particularly nice, the reward vector in that bonus question. And then you're going to have two terminal states. You're going to have two boundary conditions at 0 and at n, because those are the terminal states for the gambler. So, and if you set up that equation and you solve it with the correct boundary conditions, that will give you the answer. Okay, any questions or comments? Okay, I'm going to be here for a while. If you want to talk about Lab 1, please come ask me. And I'm extending the deadline until Wednesday. Okay. See you guys on Thursday.